Hi, this is Robert Bolaños. Welcome to the analysis and design of a flyback. This is part 23, the Opto-Coupler. Okay, so these are what we will be attempting to do. I'm going to try to explain the purpose of the Opto-Coupler and how it works. Explain some of the critical opto parameters like CTR right here, which is the current transfer ratio, the voltage LED. In other words, how much voltage does the LED have? Basically, it's the forward drop, and then the current when it's forward biased, the LED, and the bandwidth. Those are some of the parameters. And then I'm going to go and show how to connect the TL431 and how to bias it correctly. And we're going to take into account beginning of life, BOL, and then end of life. End of life is aging. Okay. And then the end is we want to build an average model and then compare to a switching model. See if this average model. Now keep in mind that the average model is used to predict the AC loop response. Okay, and this is what usually is the hardest to master. Okay. Now, you should have a little bit of a background on how to adjust or compensate the loop. I do have some videos on my webpage, and there's a section on loop compensation. I believe I have 3 videos. Watch video 1, 2, and 3 to give you a feel for how to do the loop compensation. Okay. Okay, first of all, the purpose of the optocoupler is to feedback a scale representation of your V out. Okay, and it does that by having a LED. When you forward bias the LED, it shines a little light, and there's a receiver, basically a NPN transistor, and when this light shines, that the emitter, and this is the LED, when it forward biases and shines a light on the NPN transistor, it causes current to flow. Okay, but there is a barrier. This is the isolation barrier. In other words, there's physically no contact or electrical contact. There's insulation between the LED and the transistor, okay, which is this point. It provides isolation between the primary and the secondary. Typically the LED, I'm sorry, excuse me, the LED will be on the primary, I'm sorry, the secondary, and the transistor, the NPN, will be on the primary. Okay. Now, it has some disadvantages, and the main disadvantage is that the opto is bandwidth limited. Okay. In the example that I'm using a 4N, or at least a SPICE Okay, it has a bandwidth of about 24 kilohertz, and it basically looks like a low pass filter. 25 kilohertz, 24 kilohertz, somewhere around there. Okay, here's another important point. Another disadvantage is that the CTR, the current transfer ratio, decreases with time or lifetime. In other words, as it ages or gets old, the CTR starts to decrease. Okay. Next information that is vital is that the opto, because of its bandwidth limitation, here we are. Okay, this is a pole. Okay, so it introduces a low pass filter, and it affects the response, and you need to characterize it, meaning that you need to measure what the bandwidth is. That way you can take into account. And you also can measure the CTR when you do a measurement. Okay. So what is CTR? Okay. CTR is the ratio, or the current transfer ratio. Okay, so it's a ratio, and it's actually a ratio of, in this case, you can call this out. In other words, this is the NPN. I'll call this the out, which is labeled there, divided by Vn. That's Vn. Okay. So that's this section. But you can also say that this is IE, because it's the current coming out of the emitter. Okay. So you can have this representation IE. And then, and this here would be, since this is the LED, this would be, you can either call it IN or LED. So for the rest of the lecture, I will use this terminology, IE and ILED. So that's what the turns ratio is. Okay. Now on the 4N25, an important parameter that they publish, and this is, I believe, the Vishay. This is the absolute excuse me. This is the absolute LED current rating. You can go up to 60 milliamps. So the most that they recommend is 60 milliamps. Okay, so that's, so basically you don't want, you want to stay below that. Okay, and I'll go ahead and bring it up here again. If this is a maximum, then you can derate this. Okay, and typically if you're using a diode and you're going to derate it is like a safety margin. Okay, so instead of using this at full power, this would be, the 60% would be 100%. you would not use it at 100%. Okay, you would use it at a much lower value. That way you would ensure that you have some margin. So typically on a diode, the current through a diode is typically 50%. So in this case, this IF, and I'll just call max, and then I'll say D rate. What we'll do is, it's 50% of 60 milliamps, 30 milliamps. So this is what we're going to do. We will not bias the LED D rate. It's also I LED. This is the most that we're going to pump. Okay, that way we always have enough a safety margin. Okay, so here's a spice simulation just to show how it works. I put a current source, okay, and I drove 2 milliamps into the LED, and then your collector has to be connected to VCC. In this case, VCC is 12 volts, and if you look here, I'm putting 2 milliamps, and the output, or IE, is 1.107 milliamps. So these are my measurements, and when you plug them in, this is your transfer ratio that we get. Okay, and mind you, this ratio would be at the beginning of life. Okay, that's when your CTR is at maximum. As you age, it starts dropping. Okay, and then another parameter is that when you bias 2 milliamps through this diode, you have approximately of a voltage forward drop of approximately 1 volt, which is what this is at 2 milliamps. So that's another parameter that you have to be aware of. So once we have an opto, in this case, and on a later video I will do this in the lab, and I will use a 4N25 opto because that's the spice that I have available on my simulator. So I'll see how close the spice is to the actual. So if you have a FRA, which is a frequency response analyzer, you can connect it like this. This would be the FRA. You would put a signal in here through this resistor, and these two resistors must be equal, and you put a large cap, and this can be like 100 microfarad cap, and then you bias it at the current that you want or that you will be using. In this case, we'll use 2 milliamps, or at least close to that, so you should get 1 milliamp here. And if you do that and you plot the AC plot, you'll see that it has a bandwidth. Okay, see if we can zoom in. See right there. So that is the -3 dB dB point, and that equals to 23 kilohertz. So that's something that is important and we need to be aware. Okay, so now I know this is quite a bit of information, so listen real carefully. Hopefully this will make sense. So now this is the way you hook up the TL431 and the opto. Okay. You're going to use this R1, R2, and then this is your compensation, and this is your divider network. Okay, so basically let's cover this one here. Okay, R3 and R5 are the divider network, and that's what provides a feedback. Okay, basically that point we want to set at 12 volts, and this ref should be 2.5 volts. Okay, this is from the last lecture, lecture 22. Vref, which is right there, should always be 2.5, and that's what I'm saying right here, that Vref is 2.5. And if you want 12 volts to be at the output, then we can select R5. Okay, in my example I'm going to use 5K. Okay, and we solve for R3, and you can do that basically by calculating this current, and that's easy because you set this to 5K, so it's basically 2.5 volts divided by 5K. That's this current. Well, that current should also flow through here. So now all you have to do is 12 volts minus 2.5 divided by the current. Okay, which is what this equation is. Okay, and I believe you end up with 19k ohms. Okay, let me zoom out a little bit. Okay, and this, okay, I have an error here. Let me correct that. Oh, no, it's not an error. Okay, C2, which is this, and R4, those are the integrators. It's the integrator cap and the integrator resistor and the integrator cap, and those form a 0. Okay, I think my computer's acting up a little bit. Okay, next, C1, which is this one, that is your Rolloff. However, depending on the output filter and the bandwidth, it may be omitted. Okay, we'll explore that. Okay, so we've covered the TL 431, and now we talked a little bit about the opto. So now we're going to talk about the PWM, and I'll be using a model the UC 1843. Okay, and I believe in looking over the Christopher Basso book, he has a section in the book about this. Okay, and basically I want to point to this. This is very critical. Okay, in that you have the error amp, and remember this is in the PWM. Basically, the PWM is right here. There's a error amp. Okay, it's internal, and this is the internal that I'm looking. Now, what I want to point out, which is critical, is we're going to assume, and this is the assumption, a little bit of a hand waving, and I'll offer a little bit of explanation of why. We're going to assume that V comp, this node, we're going to assume that it's 3.1 at steady state. Okay, this is the assumption. It's basically the same, that it's going to be 3.1, and the reason is this, in that internally right here there is a zener, so the maximum voltage that this node will see or can see is 1 volt. And then you have these two resistors, divider network. So if you have 1 volt and you have 2 R's, that means that you should have 2 volts here. Okay. However, on some of the UC 1842, they don't have a 2R, it's an R. Okay. Oh, I'm sorry. I said it should be 3 volts. It'd be 1 and then 2 volts. Okay, but if it's a R, then it's 2 volts. Okay, and then you have two diode drops, which is 1.5, so you end up with approximately 3.2 volts if this is a 1R, basically. Okay, so that's the statement that Basso, and it makes sense that this node would be limited at steady state to about 2.1, 2.3 okay, volts. Okay, somewhere around there. Okay, so it's an approximation. So that's very important because it simplifies our analysis. So now we're going to put everything together, and the intent is we want to do a AC model, which is what this is. This is Jack's model, Jack's Alexander. Okay, Jack model basically models the transformer, the MOSFET, the switching, basically the PWM with the current control. It's a, yes, I'm sorry, it's a current control, voltage control current source. Okay, so here's the voltage source and here's the current. Okay, so that's what that is, and this is Jack's model, so we're going to use that. And what I want to point out is that this section is the UC 1848 PWM. This is where they have the diodes, and the point where I said V comp is 3.1, we're going to go ahead and assume that this is 3.1 there. Okay. Now with that being, then what you would do is you would set the gain of the error amp that's inside the PWM. You set it to unity. And how do you do that? By making these two equal. And you make them high impedance. In my example, I'm using 100K, 100K. Okay. And this is just a high frequency Rolloff cap. Okay. Now the next thing that is critical, we're making the assumption this is going to be 3.1, and internally the non-inverting is connected to a 2.5 reference. And if you notice, this is the reference. So this is at 2.5. Okay. So I have that in the model. Okay. It's getting a little busy here. Let's see if I can. Let me go ahead and clean this up a little bit. Hopefully that you already get the idea that this is inside the PWM, and this is a representation of the AC model. So by analysis, the V, or the inverting, will try to match, I'm sorry, these two nodes will try to match each other. So then you can say that the inverting side, which is this, will also be 2.5 volts. That would be the feedback node. Okay, so that means this is more positive, so you're going to have current flowing in this direction. Okay, and these two are equal. So, and if you notice, 3.1 minus 2.5 is 0.6. Well, that current cannot go in there, so it has to flow out, so it flows in this direction. And since this current is the same as this current, and we have 0.6 voltage drop from here to here, then you can say that you're going to have a voltage drop between there and there of 0.6. Therefore, you can make a statement that this node, which is the emitter of the opto, will be 1.9. Okay, so let me just go over that again. Let me clean this up again, because this is critical in understanding. Okay, so what I'm saying is, and this is the analysis that Basso also did, is that this node is going to be 3.1, and then since this is 2.5, this is the reference, then this node is 2.5. So this current will flow through here. Okay, and since there is a drop of 0.6 volts here, then you're going to have a drop of 0.6 volts from here to here. So 2.5 minus 0.6 means that you will have that voltage there. Okay, so let me go ahead and erase this. Okay, so hopefully you understand that this is the assumption that we're saying that this V opto, we can also call it VE, is at 1.9 volts. Okay. Okay, so now we're kind of set up. So now we're going to put everything together. Okay, so now I can say that the current going through the collector, and then it comes through the emitter. Okay, that current is going through here. Okay, and although this current is very small, it's basically insignificant to this voltage or current. This is much larger. Okay, but we know that this is 1.9. Okay, so current is going to flow through here in that direction. Okay, so then you can say the statement that IE times this resistor, and I'm going to say that this is R down. Okay, so you have that equation, and then I have CTR equals IE, and then this is going to be I LED. Okay. Okay. Now here I wrote it in a different form. Okay, we're going to say that IE is equal to 1.9 volts. And it's basically also, we can also say that it's V opto. So basically these are interchangeable. VE and V opto are the same. Okay. And then what I did is I took this equation, so for IE, okay, and then since I know what this voltage is, and let me clean this up again. Okay, we know what this voltage is already, and I know that this current, where I should have some feeling what this current should be, what I want is I want the value of this resistor. Okay, so how do we do that? Okay, well, this is already known. It's 1.9 volts. Okay, so we need to figure out, okay, what IE are we going to use? Okay, so we can use this equation, substitute it, and you end up with this equation. Okay, now that equation says that it's VE, again the voltage at the emitter, divided by the CTR, and then I put BOL, which is the beginning of life, times the current through the LED, this LED, and again it's the current at the beginning of life. So let's continue. Okay, so here I have it again. Okay, now this is the CTR, beginning of life, and then we need to know what is the current that we're going to be using for the LED at beginning of life. So where do we get this? Okay, well, if you look in here, we're going to say that the current that is flowing through the LED is going to be flowing through here as well, in addition to 1 milliamp that flows through here. Okay, and we're going to set this ILED to about 2 milliamps. Okay, and we're going to set this bias to 1 milliamp. Okay, so let me describe this again a little bit, make sure this is correct. Okay, we're going to say that this current we're going to set, and this is real easy to set because the voltage drop across the LED is 1 volt, so, and 1K, so we're going to have 1 milliamp going through there, and we're going to pump 2 milliamps through here. So this is the ILED. Okay, so when you set the CTR, which is 0.5, and you set the LED to 2 milliamps, you end up with the RE, or let me be more consistent. Let's see. There's a delay when I select that resistor. You can either say that it's RE or R down. Okay, so it's the same resistor. Okay, so now here's another assumption. We already know this. We know that the V-opto or VE is 1.9 volts, and when the flyback is steady state, it will be constant. Okay, since it's a steady state, the current throughout its aging period will always be 1 milliamp, or at least very close to 1 milliamp. However, the current through the LED will change as the CTR decreases with aging. Okay, so let me go back to the schematic. Okay, so what I'm saying is, okay, let me go ahead and, what I'm saying, at steady state, once we set this current, and we're going to set this current to approximately 1 milliamp, this will be fixed. It will not change with aging. However, this current, the ILED, will increase as the CTR decreases with aging. Okay, that's very critical. This is constant. That current is constant, but this will increase. Okay, will go up. Okay, so that's very critical that you understand that part, and I'll show hopefully a simulation of that. Okay, so here I am. Can't stress enough that it's important that the LED will change as the CRT decreases with aging. So basically, IE will be constant, even when the CTR decreases and the LED goes up, okay, it will be constant. However, the LED current will increase as CTR goes down. Okay. So now this is where I kind of define the beginning of life. In the beginning of life, we'll start with a 50% duty cycle. That means that the LED will have 2 milliamps, okay, which is what we set. But then at the end of life, the CTR will decrease, okay, and the LED current will also increase. So how do we calculate this? Okay, because we want to be sure that as it ages, the LED, which is providing feedback, you want to know, you want it to keep on working, so we need to be sure that we bias it correctly. So to derate the LED per the IEEE, it says that if the maximum volt current is 60 milliamps, then you should only use it up to 30 milliamps. This is what I had mentioned up in the beginning. Okay, well, using that, that's what we're going to do. So we're going to use the criteria that the LED will change when it's new or beginning in life from 2 milliamps, and it will age and slowly it will rise up to 30 milliamps. Okay, so these are the two figures that you need to know, especially this one because that's the one that you're going to be using. So now we're going to go ahead and we just need one more resistor to calculate. We already calculated this one. This is close to 1900 ohms. I'll just spell it out, ohms. So now we need to calculate this one. Okay, so we're going to call it RUP. Okay, and see if it makes sense. Okay, so basically you have two currents. You have this I bias, which is this here, and that's going to be 1 milliamp. Okay, and we know VD between here and here is 1 volt. Okay, so now we can write this equation. So you have V out, and we'll neglect this because there's this AC, and then we have this resistor, and that resistor has both currents. Has this current, it has the I LED and this bias. Okay, so this is summed here, but you also have the drop across VD, basically that the LED. So this is the LED. Okay, so you have this equation. Okay, so at the beginning of life, this node, which is the cathode to analog, so it's VKA, we can say that VKA will be around 10 volts. Okay, and then at the end of life, as the CTR decreases, LED is going to go up, then this voltage VKA will decrease, and this will decrease to about 3 volts. So we don't want this thing, that node, to be lower than 3 volts, because once it gets below 3 volts, then the TL431 does not regulate. Okay, actually it will regulate down to 2.5, but I'm using a little safety margin. So we're going to say that we want this node VKA at 3 volts. Okay, so now we can solve for RP up. Now we have this design equation. Okay, so this is 12 volts, this is V out, VD, this is the LED, that's going to be 1 volt, and then VKA, we said that we want that at 3 volts. Okay, and then we know that this is 1 milliamp, and then we want the current through the LED, but at the end of life. Okay, so that's 30 milliamps. Okay, so then we have the numbers here, and we have 225 ohms. Okay, so let's see if this is correct. Okay, so let me erase this. So this is the resistor that we initially calculated, which is 1900, and then this is R54. This is the pull up. Okay, so now right here I have this term in the curly brackets. I named it CTR, which is the current transfer ratio of the model. So I have a statement here. This is the CTR, and this corresponds to 50%. Although it says 0.0015, it's actually 50%. Okay, and that comes from this statement right here. There's a multiplier, but this is the beginning of life, and we're gonna go ahead and run it with a CTR of about 50% or 0.5. So when we run it, okay, we get a Bode plot, but what is more important is I want to look at the voltages. Okay, and if you notice here, okay, we said that the V comp, this is the V comp, we wanted 3.1, and then I said that the voltage at this node would be 2.5, and this would be equal, so basically it's almost equal. And then I said that the difference between here and here is 0.6, then you could subtract 0.6 from 2.5 and you end up with basically 1.9. Okay, so we have that there. Okay, so now if you notice, the current that's going through here is basically 1 milliamp. That current goes through the transistor and shows up here as 1 milliamp. Okay, so if you do that, 1 milliamp, then you should have approximately close to 2 milliamps going through here. So if you notice this voltage source, this is a placeholder to measure current. This was supposed to be 2 milliamps. It's 1.8, which is close enough. Okay, and you have basically almost 1 volt difference between here and here. So that means you have 1 milliamp here. So here's the summation of this current and the current going through the LED. It's close to 3 milliamps. This is what I calculated. It's 2.8. Okay, and I mentioned that at the beginning of life, let's see if I can bring this. Okay, I made some assumptions. Okay, so I said that this voltage VKA, which is right here at the beginning of life, would be close to 10 volts, and it is. Okay, so everything matches. Okay, so now let's do a simulation, and then we want to see how, by changing the CTR, which would mimic aging, what happens. Okay, so now we're going to go ahead and we'll put a comment here, and then this will be actually a CTR of almost 3%, basically very, very low current. Okay, and that would be the representation of end of life. So this would be after a long aging process. Okay, so now we'll go ahead and keep in mind that this, I made an assumption. I said that this current will stay the same. So I'm not expecting this to move too much. And I said that this current going through here should increase. And I calculated it should be close to 30. So let's go ahead, run it. Okay, still runs. So now we look in here, and if you look, the current through here remains constant. Okay, basically 1 milliamp, close to 1 milliamp. Now remember, this used to be 2 milliamps. Now it went up to 27, almost a 30. Okay, and then that with the 1 over here, you got 29. And then I mentioned that this voltage at VKA was, we wanted it close to 3, and I believe that's what I mentioned. It's very close to the 3. It's higher, so we have a little bit of safety margin. Okay, so this is how you know that this thing is regulating. And if you look up here, you have 12 volts. Okay, so now let's take one more before we wrap this thing up. Okay, I want to do a Bode plot to show the effects of aging. So here I have CTR. So I have the beginning of life CTR and the end of life CTR. Okay, and I want to show what happens to the bandwidth. Okay, so this is the crossover, and it's crossing over at about 10, 20, 30 kilohertz. This is at beginning of life, and then when it ages, the bandwidth decreases, and it drops down to almost 2 kilohertz. This is after it has ages. It has age. Okay, so that's important. That you want to make sure that you can bias it over a long or a wide variation of CTR. I think that will be enough for tonight, and on the next one we'll start compensating to make sure we have a good loop response, and we'll compare it with a switching model. If you have any questions, you can email them to me, or you can post them online on my video channel. Thank you for watching.